Day 2. Okay, folks, so here we are going into Day 2, and you should have this sheet entitled 6-1 Slope Fields Day 2. So in our intro, what is a differential equation? It is an equation showing the instantaneous rate of change. For a given function. So an example could be dy dx is equal to negative y over x. So here we have a derivative. This is considered to be a differential equation. Now if they ask us to solve a differential equation, it's really important to know what are you finding. And what we're trying to do is we're trying to find the function or trying to find y. Okay, and that's going to be the scope of the Day 2 part, which is solving a differential equation, which again, right here, we will be using a special technique in second semester to do this. Today we're simply going to be revisiting famous derivatives that we've come to know and love and finding their antiderivative, finding the function that has a stated derivative. So here we go. Sounds like a great time here on this wonderful snow day that we're having. So we're going to find the general solution. Again, the solution is solving the differential equation. We're going to find the function that has the exact derivative that's stated. So I'm going to give you a second to do that. Let's take a look at this. Again, this is a derivative that has a couple pieces to it. So my hint to you is to take this piece by piece to try to find the function that has this interesting derivative. Give that a shot. So here we are. We're going to take a look and we're going to find the function that has this derivative. So I'm going to start out y is equal. And this piece right here, this is something that should just be screaming at you what has this derivative. So again, I've got a ratio. I'm wondering if it could be an ln. No, it's not, because the derivative at the bottom is not on the top. So again, when I have ratios, you want to know, okay, yeah, those inverse trig functions were famous for having derivatives that were ratios. So again, this will be on a DQ. It's been on ones in the past, and it will be on others coming up fast and quick here. So again, hopefully you recognize that this is the inverse sine function with the stated derivative that we see right here. Here, this one, again, is not an ln. It is not one of the inverse trig functions. I'm going to choose to write this as negative x to the 1/2. I love polynomials. They're easy to find derivatives as well as to anti-differentiate. So again, my degree is going to go up by 1. And again, let me fix this right here. That should be a negative because, again, the square root is in the denominator. So if I add 1 to the numerator, I'm going to get x to the 1/2. And in terms of what I need in front, I'm going to need a negative 2. So again, 1/2 times negative 2 is going to give me a leading term of negative 1, which is what I have right here. So this would be the general solution. General, I'm finding the family of functions with this derivative. So please, for the love of calculus, do not forget to put your plus c to represent the family of functions with the stated derivative. And again, I'm hoping that we can soon come to a consensus on the official c for the class of 2014. So we can dazzle our AP readers with very fancy, impressive constants of integration. So here we are in example 2. We have the change in y with respect to t. So the change in y over the change in t. So instead of y and x, we have y and t. No big deal. And I've got the ratio of 1 over t plus 4. And here they're giving me an initial value. So what I immediately know is I'm going to need to show solving for c. Okay, and this is a really important thing to get good at. It's a hot topic on the AP exam. So I'm going to give you a second to see if you can find the function that has this derivative. And don't forget your plus c, and then go ahead and solve for c. Alright, so here we go. Hopefully you had some success with this. So let's walk through it. So again, I've got a ratio. Much like I did up here, I had a ratio. And this one we quickly realized that this was the inverse sine. And here, the derivative of the bottom is the top. It's a 1. So I recognize this to be a ln. So y is going to equal ln of my stuff, t plus 4. And I'm going to put my plus c to represent the family of functions with the stated derivative. Now what's really important to know is that ln's we know have restricted domains. So I'm going to make sure that I put that over here that t has to be greater than -4. I can't take the ln of 0, and if t is -4, I'm getting ln of 0. So anything greater than the -4 is going to produce a positive value. And now I'm going to solve for c. So again, y, when I put -3 into the y function, I get out at 2. So I'm going to put in a 2 for y. I'm going to put in that -3. And there's my c. So I get 2 is equal to ln of 1 plus c. And we all know that ln of 1 is 0. So I get 2 is equal to c. So again, I'm going to go back to the problem, solve the initial value problem analytically. We've done that. We found the antiderivative. We plugged in our value for t, our value for y. So I'm just going to make this really clear over here that y is equal to the ln of t plus 4, where the constant was 2. And I'm going to make it really clear that there is a restriction on this function, and that would be that t is greater than -4. Alright, so I know you guys are always up for something crazy here, and we're just going to try to make some connections here. So what we found is that our derivative, dy dt, was equal to 1 over t plus 4. And we found the function y is equal to the ln of t plus 4 plus 2. And I'm going to just put down here that t must be greater than -4. So what we're going to do is we're just going to try to tie together lesson 1 and lesson 2. And we're going to take a look at the slope field for this problem. So again, my slope field is going to go into y1. Let's get that fired up. And there it is. I've got 1 over x plus 4. And y2, I'm going to put ln of x plus 4 plus 2. I'm going to go to my program key. I'm going to go down to slope field, SF, enter, enter, enter. And it is quickly going to generate slope fields. And it probably would have been wise for me to change the window going from -4 to infinity. And what I'm going to need to do is just, this is a problem with the program, is it's going to need to turn on the function that I want to put on top of my slope field. I want to see if it does model the fields nicely. So again, as I look here, I've got a vertical tangent right here, and that makes sense for an ln. Remember, a ln is the inverse of an exponential. And following those slope fields, it's going with the flow. So again, this is an important AP topic. I think it's one that you'll do well with as you work on this lesson from home. Do message me if you have any questions at all, and we'll try to make this work so that we don't fall any further behind. Do phone a friend, Skype, type any resources on YouTube if you need further examples. Here's our day 2 book problems right here. If you don't have the programs, I wouldn't sweat that. I don't think a lot of what we are going to be doing is going to require this. Just I think this is a really nice interpretation to get the slope field from the derivative, plotting our solution to make sure that it models what we're seeing in the slope field. If you don't have this, you can get it from me when you get back. And again, want to wish you luck as you're working on your lesson, and hope this goes well. And look forward to seeing you guys soon. And we'll talk then. Good luck.